Hello everyone, we are Group 6. I am Ding Youchen, and for members, we have He Chenyuan and Chen Zhenwei. For this course final project, we choose Scaffold GS Structured 3D Gaussians for View Adaptive Rendering as the selected paper, and this paper is from this year's CVPR. And for today's outline, we have the introduction, method, experiment, ablation studies, which stand for our experiment, and the final conclusion. And now let's get to the introduction part. For nowadays most popular 3D reconstruction way, it must be the 3D Gaussian. It demonstrates state-of-the-art visual quality and the real-time rendering on several established data sets. It has main three key elements. The 3D Gaussian splatting represent the scene with 3D Gaussians that preserve properties of volumetric radiance fields for scene optimization. They also interleave optimization control of the 3D Gaussian. It developed a fast visibility-aware rendering algorithm that supports an isotropic splattering. Now let's talk about the difference between the two of them. For vanilla 3D Gaussians, splatting is suffers from heavily redundant Gaussians that try to fit every training view. They also neglect the underlying scene geometry. And for scaffold Gaussian splatting, it represents the scene using a set of 3D Gaussians structured in a dual-layered hierarchy. It also uses anchor points to distribute local 3D Gaussians. The scaffold Gaussian splatting predicts their attributes on the fly based on viewing direction and distance within the view frustum. And now let's talk about the contribution of this selected paper. This paper represents the scene using a set of 3D Gaussians structured in a dual-layered hierarchy, which reduce the storage size. It also uses anchor points to distribute local 3D Gaussians, developed anchor growing pruning strategy based on the importance of the neural Gaussians. The position of the anchor are more similar to the underlying scene geometry, which reliably improve the scene coverage. It also predicts their attributes based on the viewing direction and distance within view frustum, which leads to more robust novel view synthesis. After introduction, let's get to the method part. For vanilla 3D Gaussian splatting, it represents a scene by many 3D Gaussians, and for each 3D Gaussians, it has four main variables. The first one is the mean, which means the position of the Gaussian. The second one is the scale and the rotation. It is the covariance of the Gaussian. The third one is the color. It represents by three-level spherical harmonic. And the fourth one is the opacity. And for scaffold Gaussian splatting, it represents a scene by anchors, by many anchors. And for anchors, it represents K Gaussians. For each anchor, it also has four main variables. The first one is the anchor position. The second one is the offset. It represents the relative position of each Gaussian and the anchor position. And from this figure, we can see that the black dot is the anchor. And for this anchor, it has K 3D Gaussians. And for offset, we can get the Gaussian position. The position of the neural Gaussians are calculated as the below function. And X means the position of the anchor, and O means the offset, and L means the scaling. And the third variable is the scaling, and the fourth variable is the feature. The feature decodes the shape, opacity, and the colors by MLP's decoder. Since all the Gaussians in an anchor share one feature, so the storage size will be less smaller compared to the vanilla 3D Gaussians. And this is a more specific calculation of the parameters. We can see that for vanilla 3D Gaussian splatting, it has means covariance, which means the rotation and the scale. And the third variable is the color and the opacity. So the total parameter is a 65, and for K Gaussian it is 65K. And for scaffold Gaussian splatting, we suppose that there are K Gaussian in an anchor, and for every K Gaussians, it has four variables: anchor position, offset, feature, and scaling. So the total parameter for anchor, which stands for K Gaussian, is 3K plus 38, and which is less smaller than 65K. And the anchor point initialization. The author used the sparse point cloud from CoMap as the initial input and then voxelized the scene from this point cloud. The center of each voxel that contains points is treated as an anchor point. And this is the slide for the calculation of the position of Gaussian. The author supposed that the attributes may be changed between different viewpoints. Therefore, we decode the attributes not only from the anchor feature, but also the relative viewing distance and direction. For this figure, it shows that for each feature, it goes through three different MLPs decoder to decode to get the opacity, color, and scale and rotation. And for this figure, it shows that the decoded attributes of a single neural Gaussian observes at different positions. This pattern indicates that attributes of a neural Gaussian adapt to viewpoint changing while exhibiting a certain degree of local continuity. Since neural Gaussians are closely tied to their anchor points, which are initialized from structure from motion points, and this poses challenges to the initial placement of anchor points, especially in textureless and less observed areas. We therefore propose an error-based anchor growing policy that grows new anchors where neural Gaussians find significant. After the method, let's talk about the experiment which the author did. The author did an experiment on the real-world data set to compare to the previous work, which is the 3D Gaussian splatting. We can easily see that the PSNR has, for scaffold Gaussian, it has better PSNR score than 3D Gaussian splatting. And also, it has the faster rendering speed. Not only the PSNR score and the rendering speed, it also has the less storage size. The author also did an opacity visualization experiment. In scaffold Gaussian splatting, only the opacity of the Gaussians over threshold will be activated to render the scene, and the below image shows the Gaussians that are activated in this view angle. We can see that the distribution of Gaussians are more similar to the underlying scene geometry. After talking about the experiment which author did, let's talk about the ablation study we did. What we did is the feature augmentation. In this paper, there is only one shared feature for one anchor point, and it is shared for three kinds of attributes. Without that, these three attributes may not have strong correlation with each other, so we try to learn three different features for these three attributes. And this is our experiment setting. For the original scaffold Gaussian splatting, we used the same feature to go through different MLPs decoder. For our own experiment, we now learn three features for one anchor and feed them into different MLPs decoder to get the color feature, scale and rotation feature, opacity feature, and each feature dimension is 32. We then use this experimenting setting to test on the synthetic nerve data set. And this is our result. We can see that the PSNR score improves 0.2 dB with three features. However, it also requires more resources. We can see that the learnable parameters change from 32 to 96. Last experiment shows that the visual quality will increase by using three different features, but it also costs more resources. Therefore, we try to allocate more resource to the original setting. that is, increase the feature dimension of original feature. As the table shows, we found that if we use shared feature and increase the feature dimension to 48, the visual quality will also improve too. And the PSNR score even passed our previous setting, 3 features for 3 different attributes. Therefore, we can tell that there are still some shared information between these 3 features. And now let's get to the conclusion. Scaffold Gaussian splatting proposes a dual-layer hierarchy representation for efficient view adaptive rendering. Its structural arrangement makes the distribution of Gaussians with opacity over threshold more similar to the underlying scene geometry. They also show that the anchor points encode local features in a meaningful way that exhibits semantic patterns to some degree. And this is the limitation. Scaffold Gaussian splatting has shown that its distribution of anchors more are similar to the underlying scene geometry. And the author also mentioned that this method has the potential to compose different scenes. However, different scenes show different MLPs for scaffold Gaussian splatting. Therefore, we think maybe designing a general decoder may help for this kind of task. And this is our project. Thank you.